All right, so today is the last lecture on piping systems. I'm going to cover a variety of topics that I feel are practically important, even though you may not find them in chapter 1 of the textbook, but they are fair game for the exam, which is on Thursday. Yeah, so 1 week from, not 1 week, 2 days from, 2 days, okay? So let's jump into it. So we talked last time about the process. I want to summarize the design process as well. We're going to talk about head loss again. We need to be able to do it by equations. We need to be able to do it by hand. But then engineers use not only software, which I showed you, there's plenty of that software out there, as well as charts. And once you see the charts in the software, you say, hey, that's pretty good. So I want to make sure and expose you to that. We talk about design loads and capacity. Remember, that was the start of the process. But then if you're responsible for providing cooling to this campus, you're going to have excess capacity as a design engineer. You're not going to get caught flat-footed. All right. Talk about load diversity. That's an important concept, as well as turn-down ratio, because some days it's not the extreme day of the year, is it? But you design to the worst day or the most extreme day of the year within 0.4%. Then on a campus, you'll have multiple chillers, which will give you that great turn-down ratio so that your capacity can match the load, or the what you supply matches load. Control valves are very important. We could spend a lot of time on control valves, but I'll just emphasize the flow coefficient as well as the authority. I think I mentioned the authority of the flow valve, control valve is important. And then we'll talk about the design of a control valve such that you get an equal percentage of what you're trying to control, such that if the control valve goes to 50%, you actually get 50% of what you're trying to control. That may seem like a funny idea, but it's real. And then the last, because we're going to get into heat exchangers and heat transfer analysis after the first exam, we talk about heat emission from a coil. Either you're putting cold water through a coil to drop the temperature of air, or you're putting hot steam or hot water through a coil to increase the temperature of air. And so those are need to be controlled by engineers. And that's a great example where you have an equal percentage control valve. That's our outline. Let's get going. So this is a summary. For a new system, when you're designing a new system on paper, get the load calcs done. How much cooling and heating do I need on those extreme summer days and extreme winter days? Then calculate your flow rates. You're going to do the same thing for steam flow rates or hot water flow rates for the winter day, but you're going to do it also for chilled water for the summer day. Do the layouts, how long they are, where do they need to go, how are you going to route it. Basically select the pipe. It's going to be a steel or copper or PVC, and then essentially the diameter. Here's the recommendation, because a lot of times it's like, I'm lost, what do I do? Well, don't go too slow and don't go too fast. You want it to go up to about 4 foot per second if you have a small pipe, and a pressure drop of anywhere from 1 to 4 or 0.75 to 4 foot of head per 100 foot of pipe length for 2-inch or larger pipe. There you go. If you want to do a scoping calculation, multiply the physical length by about 1.5 for the equivalent length, and then you can do some scoping calcs. And then later, if you're doing the more refined design, you can go ahead and be more accurate. And then never forget how to calculate that head loss. The head loss is your major plus your minor. Do you understand my F L over D times this head velocity and this K times the head velocity? And if you just ravel everything into an equivalent length, then it's just L cubed. So the head loss, never forget, is proportional to the head velocity primarily. And the head velocity goes as something like velocity squared or flow rate squared, volumetric flow rate squared. And we saw that in the Hayes and Williams correlation or equation. And then size your pumps and motors. Be careful. The work that goes into the fluid, you put a shaft work into a device called a pump, but not 100% of it gets into the fluid. Often you calculate what needs to get into the fluid. Hence, I size the motor to drive the pump based on the efficiency of the pump. And so shaft power and the fluid power, that's the efficiency of the pump. Then what you supply electrically to the motor, not 100% of it goes in shaft power either, so you have the efficiency of the pump, motor. So don't forget when you size pumps and motors to account for their efficiencies, even though the efficiency of the motor can be quite high. Well, that's what we covered last time, didn't we? Here's a simple expression for the rate of heat transfer to or from water. So we say this is the rate of heat transfer in BTUs per hour. It's a constant 500 times the temperature change in degree F times the gallons per minute flow rate. Can you show that that correct equation is correct? Could you derive that equation? If I gave you a blank sheet of paper and said, show me that this is the correct equation with units. So here it is, shown. We start with Q dot is equal to M dot C sub P delta T. What is that? I have one control volume. I have an inlet flow, inlet 1, outlet 2. The fluid is undergoing a change in temperature or a change in enthalpy. We go back to the first law of thermodynamics. You can either go and think about it being either heated or cooled, either one. Whatever that Q dot is, if it's a delta T increase, it was being heated. If it's a delta T decrease, it was being cooled. It's always liquid water. So the change in the enthalpy from H2 minus H1 is approximated C sub P T2 minus T1. True? Just write the first law for a system. Okay? And so the Q dot, the rate of heat transfer, is equal to the mass flow rate times the change in enthalpy. If you're thinking about Q dot in, then that's equal to the mass flow rate specific heat, T2 minus T1. And then you just expand M dot. M dot's just the density times the flow rate. But I'm going to give the flow rate in gallons per minute, and I'm going to give the temperature change in degrees F. Hence, I use the density of the liquid water. I use the specific heat of liquid water. That truly is 1 BTU per pound mass degree F. Then I use this. What's this? It says 1 cubic foot of volume is 7.48 gallons of volume. Think about that. You buy a gallon of milk, you know what a gallon feels like, looks like, about the size of it visually. Then you think about a cubic foot. You could actually pour 7.5 gallons into a cubic foot. There's a lot of volume in a cubic foot. And then what is this one? It's even easier. So really there's only 2 unit conversions. You have to know the density of water, and you have to know the specific heat of water, and the first law of thermodynamics, and you got it. Now, if you run with these numbers, it comes off to 506 something. But, you know, maybe they said it was 62.3 pounds per cubic foot. I didn't go exploring. Maybe it's a little cooler water. Okay? How about the same thing for air? I have airflow, not water, and I'm heating it, and I have inlet state 1 and outlet state 2 from first law of thermodynamics, constant system. There's no shaft work or anything. It's this Q dot in is equal to the mass flow rate constant times H2 minus H1. We approximate that as C sub P T2 minus T1, which is a great approximation for something like an ideal gas like air. And we just have to use the average value of specific heat. the mass flow rate's the density times the volumetric flow rate. I'm going to put it as AV. You could still use Q. Put Q, okay, because Q we used for volumetric flow rate. Then we have the delta T, and now I have to put the C sub P with some unit conversion factors. And I'll be able to reestablish an equation that says BTUs per hour equal to 1.08 delta T in degrees F and flow rate in CFM. So what does this equation neglect? What does it neglect? Well, let's say the air is moist and I'm bringing it in to a system that's pulling a lot of heat out of it. It's cooling it. It's cooling it. And then it goes out like this. What could happen from 1 to 2 for moist air, not dry air, which would be very important from an energy balance perspective? Yeah, you could condense. Some moist air has some water vapor and it could condense. And that happens all the time in Houston, etc., down in the southeast part of the United States, and all over our coils, evaporator coils and air conditioning system, there's water coming off of them. True? Dripping all the time. In your home, business, window units, you see it. Now, if you go to El Paso, you don't see the dripping. It's drier air. Go to Houston, it's dripping all over the place, right? All right. So that's what's neglected. This is just what they call sensible, not hidden or latent heat associated with the evaporation or condensation of moisture with the air. It's the sensible heating or cooling, which means if I dump some heat in, the temperature rises. That makes sense. If I take some heat out, the temperature drops. That makes sense. That's why it's sensible. Latent, hidden, hard to understand. Okay. Show that that equation's correct. Same thing that was done before. And you just have to get the mass density of dry air. And 0.075 pounds per cubic foot is a good number. It's used all the time. It's the number for air at this PSI. What do you recognize about that pressure? 14.7 PSI. Atmospheric pressure. And this temperature, it's not too hot, not too cold. It's 68, close to 70. And that'll give you that number for mass density. Go use the ideal gas equation, right? And then what about this specific heat? Well, that you can get out of the table in your appendix, just like you did the specific heat for liquid water. And there's just a simple conversion factor. And the equation, you can reproduce this number. It's close. Maybe I don't, play with a little bit. Is it 0.749, pounds per cubic foot to get it to match 1.08? It's close enough, in my opinion. You see how we did that? So these simple equations, we know the limitations. We know, sometimes what they neglect, and sometimes what they neglect is very important, and we don't want to neglect it. And so when you have water condensation, that is talked about like a latent load on the coil. That's the jargon out there. Okay. Head loss. We talked about doing it by hand. We talked about doing it with software. And I should expose you to some simple charts because there's a lot of charts out there. Well, it's the same thing. It's the same exact thing. But you can double, triple check your work. Here they're showing you for Schedule 40 steel pipe, water at 68 degrees F. They're showing you the gallons per minute over a huge range. I mean, this is a wide range of gallons per minute. And they're saying if you pick to do it with the 1-inch pipe or a 2-inch pipe, here is the 2-inch right there, right? Where's the 1-inch? There's the 1-inch right there. Look how easy it is if I want to push 10 GPM through a 2-inch pipe. I'm only going to have a friction loss of 0.1 head loss per 100 foot of, The pressure drop, it's PSI per 100 foot. Sometimes they'll quote it in foot per 100 foot. Sometimes they'll quote it PSI per 100 foot. Here this is PSI per 100 foot, so 0.1 PSI. Let's say I want the same 10 GPM and I want to put it through a 1-inch pipe. What is that number? 3 PSI. Isn't that quite a dramatic change? All I did was go from a 2-inch diameter pipe to a 1-inch diameter pipe. That's a dramatic increase in pressure, isn't it? The pressure loss. So yeah, it's true. This came out of a website, Engineering Toolbox. I try to put a couple little footnotes like that so you can take a look. But whenever you go to a website like that, they had this little footnote. I grabbed it and expanded it. The diagram below indicates friction loss for water flow through, and then they give you a reference, ANSI ASME standard Schedule 40 steel pipes, which is nice. The pressure drops are calculated using the Darcy-Weisbach equation. That's great. That's the same equation you do by hand. And you say, oh, it's water, Schedule 40. The temperature of the water is 20 degrees, 68 F. Density of water, 998.3 kilograms per meter cubed, 62.0 pounds per cubic foot. The kinematic viscosity is given both in meters squared per second Stokes as well as foot squared per second, and a pipe roughness coefficient 4.5 times 10 to the fifth. All right. Do you see a minor typo? Okay. They didn't put any units on the roughness. So you could then compare it with other things. What do you guess it could be? Feet or meters? That's probably my guess, right? Feet or meters, because they do seem to have degrees C and the SI units first. So it may be more meter than foot. All right. Anybody else see anything else? Nothing? What about this line right there? Focus in on density. It's pound mass, yeah. But it's to 3 significant digits. You know, you've had me, I think most of you had me in the class before, and I really don't like it when I get 5 and 6, 7 significant digits to an answer, right? Yesterday, a student came in and he said, okay, here's my age to 5 significant digits, and he told it to me. And in 7 days, it'll change that digit on the 5th significant. Every 7 days, I think we calculated his age is going to get updated to 5 significant digits. Okay? So, but anyway, does anybody see it or not? Yeah, so it's not the SI unit that's wrong. At 20 degrees C, what is the density, or 68 degrees F, what's the density of liquid water? Is 62.0 or 62 point some change? Yeah, it's closer to 0.4. They didn't even get the density of water to 3 significant digits correct on this. Okay, they just dropped it. I'm not picking on them, it's just I'm picking on them, I guess. Okay, fine. But as an engineer, you know you become very skeptical, true? As an engineer. I was told by attorneys that they don't want to put engineers usually on juries because the engineer is hard to get a conviction out of, because they'll think outside the box and, you know, well, this could happen. And so if you're trying to get somebody off the hook, they'll throw an engineer on the jury. If they're trying to get a conviction, they boot the engineer off. Anyway, so we continue on. I like these charts. These charts, you can find them even in the publisher in a textbook. I found it nice and clean. So here it is. The chart is for steel pipe. You want your friction loss data in GPM or cubic feet per second for the flow rate. If you're forcing it to a 3/4 inch or a 1 inch or 1 1/4 or 1 1/2, and so you have a lot of information. Velocity, you have the velocity head loss in foot of water per 100 foot length, or the friction pressure loss in PSI per 100 foot length. So there's just a lot of information in the chart like this. And also what they do is they sort of truncate. This is no man's land. Sure, you could, here, right in here, sure, you could put 3 GPM through a 1.5 inch pipe, but nobody would want to. It's too big of a pipe. Okay? So it helps you kind of like, this is, if you're running with a 1.5 inch pipe, you know, kind of the minimum GPM would be 6 is a design, and the maximum I don't think I have it, but they stop this one here. Like if you really want to push 25 GPM, don't put it through a 3/4 inch pipe. It's just too small, right? You're going to be paying a lot. And look how that velocity goes up and the friction factor, the head loss goes up. So that's one of the things I like. Notice that we ran this Bell Gossett system sizer code last time, and for comparison, these numbers right here for a 10 GPM in a 1.5 inch water pipe, steel pipe, that from the software is exactly 1.58, good to 3 significant digits. But to the friction loss, the software gave 0.81, and this gave 0.78. That's not agreement to 2 significant digits, is it? So what gives? Well, first of all, most engineers are saying that's the same number in my opinion. Okay? So what do you think is the reason? They had to implement the Moody chart, and there's some uncertainty there. It's not like it was known to infinite precision. It's a compilation of a lot of data. And then what is the exact friction factor for that steel pipe? Because you're probably in the transition region where relative roughness and Reynolds number come into play. All right. So here is that system sizer to confirm that if you run this 1.5 inch steel pipe with the 10 GPM, you get the same, the 3 significant digits, the same velocity, but not that friction loss. And they tell you what the relative roughness is here, so you could try to back out what is the roughness for that wall of the pipe. But I didn't go exploring what was the relative roughness or the roughness for that steel pipe there. Here it is for PVC, plastic. And again, I like it where they just stop. You know, they just don't use a 1 inch for that high a flow rate, etc. Last time we talked about the design load. Typically it's the worst day measured as like 0.4% hours of the year. It's going to be colder or hotter. It's summer and winter. But these factors make sense to engineers. Diversity factor. It's the ratio. I mean, we could give it a label, DF. DF is defined as the actual load divided by the design load. So you need so much cooling, maybe I'd draw it as Q dot or something, Q dot, divided by Q dot design or worst, right? Design indicates kind of the extreme. And a lot of days, we are not hitting that design. We're not maxing out our machinery. We're quite below it. So the diversity factor needs to be able to, our equipment needs to be able to handle. Just think, if you turned it on and as much heat went in as the coldest day of the year, you'd be sweating most winter days, right? It'd be unbearable, etc. So the turn down ratio is you have the minimum capacity of that piece of equipment or that system compared to the design capacity of that piece of equipment or of that system. The turn down ratio, these make sense. So in a real design, we would have multiple chillers supplying through a manifold chilled water that would go out. They're showing it in the red line going out through being pumped out to be the heat removal devices, air handling units, and then back again. Well, so you take a look at this system. It has only two, and so there's 480 tons and 320 tons. So what is the design load or capacity of that system? Well, the answer is it's 800 tons, isn't it? If each chiller has a 25% turn-down ratio, what is the lowest actual load possible? Well, you have a very mild day. You need very little cooling out there in the campus. How low can you go? How low can you go? Well, you could turn this one down to 25% of 480 ton, or you could turn it off. But you can't turn it down more. That's often, they don't work. The efficiencies will start to degrade, but also you could have some problems with ice inside the system, inside the chillers. So the design manufacturers say, don't go below 25% or some other number of our rated capacity. So what you would do is you'd say, well, if I want to go as low, I'll shut off the big unit and I'll take the smallest unit and turn it down to its maximum amount, which means I could get down to 80 tons of cooling with this two-chiller system. So for the campus, what's the turn-down ratio? What was the max? 800 down to 8. So it's a 10%. 10% turn-down ratio. Well, this is an old map of our campus, and you probably have seen this building out here. This is the UC area. You can walk out, and there's the thermal energy plant. What do? They make hot water when they want heating, and they make chilled water when they want cooling in buildings. And they're actually always making both. It's just a relative different proportion. So in the middle of summer, they're making hot water, boiler running, and sending it out. And they have to distribute chilled water. That one plant was the only plant on campus for a very long time. And it feeds not just 2 or 3 or 4 buildings. It used to feed all the buildings. So it would come over here, all these buildings, and there's not a minimum. I mean, there's a lot of cooling required on campus in the hot days in August. And so there's some significant pipes laid to distribute it. But if you go inside that thermal energy plant, there's a door here. If you look inside, you'll see a row of chillers. This is a York chiller manufactured by York. And then there's another chiller, I don't know who it's manufactured by, but you have a 1,500 ton chiller, 2,000 ton, 3,000 ton, 2,000 ton, 1,000 ton chiller. And over there, they used to just run a few of them at a time or one at a time. But if they needed to, they could run them all at the same time and really put out cooling. So for UTSA campus, whenever I went over there last, this is a couple years old, what is the design capacity of the thermal energy plant? You just add them up and you say almost 10,000 tons. If each chiller has a 25% turn down ratio, what's the lowest actual load possible? Well, you would say, give me the smallest chiller, here's 1,000, and give me 25% of it, 250 tons. So what's the campus turn down ratio? All the way from 100% down to 2.67 or 2.6%. That's pretty good. So it can match the load. Now let's talk about control valves. So here are 3 illustrations. We have a line S and a line R. What do you think the S stands for? Supply. And then R for return. And so we have a load here, air handling unit, heat exchanger. Maybe we bring in chilled water, and now it's going to be warm water and needs to go back to the plant to be chilled again. And this is just a heat exchanger. So in the heat exchanger, you have what's right here indicated. It's a control valve. Now there's a number of different symbols. So this would be a control valve. If they put a dot in here, it's like a balancing valve. If they put a manual handle out here, it's manually operated. I forget the symbol, but this symbol, it's all not that important, but it looks like it's pneumatically controlled. So air controls it. Air with a big diaphragm has a lot of power to make that valve come and go. All right, but it's a control valve. This ins and outs does it have? Just one in and one out, and it's. But you could have another way of controlling the flow through the heat exchanger. And you could have what they call bypass and a balancing valve, and then a three-way valve, which is mixing. And so this three-way valve is controlled, and it can control such that the flow from A to the output AB is very minimum restriction, hence the load gets a lot of the flow, or it controls it such that there's a high restriction from A to the outlet, and hence it'll want to bypass. And so you'll see a lot of three-way mixing valves out in practice. You could also theoretically have a three-way diverting valve. It's up here. Conceptually, it would be not much different at all, but it's internally more complex in the design and expensive to manufacture. Hence, if you see a three-way valve, it's typically like, no, it's not a diverting valve. Those are rare. It's a mixing valve. Okay? So a three-way valve. What's the objective of a control valve? Limit the flow. Control the flow rate through the device that you want to control the flow rate. Sizing a control valve. Here's a load. Here's a valve. For stable control, the pressure drop in the control valve at full open, not when it's partially closed or fully closed, but when it's fully open, should be no less than blank the pressure drop in the branch. So this is the pressure drop in the load, we call that the branch, and then we're going to have the pressure drop in the fully open control valve. What percentage is this? Is this 10 and this is 90? Or is this 25 and 75? So what answer works? What answer is the best answer? 50%. That's a lot. Well, so that you have good control, so that when you're telling that control valve to start turning down the flow, it has the authority to do it. It has a significant pressure drop from full. It's only going to go up from fully open. So it's remarkable the first time you say, isn't that wasteful? Well, yeah, get rid of the control valve and put a variable speed drive on there and control it that way. So we have a valve flow coefficient is a metric of the strength of that control valve. And here's the equation for it. CV is equal to Q, the square root of SG divided by delta P, where SG is the specific gravity. Okay, if we're doing something else other than water, then we have to consider it. But for water, the specific gravity is 1. Stays close to 1. So you can just kind of blank that out. It's just 1 for water. So what do we have? We have this valve flow coefficient. It's the flow coefficient or flow capacity rating of that valve. Q is the flow rate in gallons per minute. Delta P is the pressure across the valve, the pressure drop in PSI. So this is GPM, that's PSI. So you could rewrite this equation that would say the delta P is equal to Q divided by CV squared. Is that correct or not? Right? All right. This is typically for the 60-degree F water, and flow per minute, gallons per minute, a valve with a pressure drop of 1 psi. Here, if you do have if you put in a 1 psi pressure drop across that valve, the square root of 1 is 1. And so the CV is numerically equal to the GPM, the gallons flow. Sometimes that's what they're saying right here. But here's a question. If the CV is 15, what will the pressure drop across the valve be for a flow rate of 30 GPM of 60 degree F water? Don't change it, it's just our standard water. What would it be? And you would just go to this equation and you'd say, well, what was my gallons per minute? 30. What is my flow coefficient? 15. And 2 squared is 4, and so it's 4 psi. Let's press forward. Here's the valve authority. Authority, I mentioned this before, is the ratio of the pressure drop across a control valve compared to the total pressure drop across the whole system. This is out of a different illustration. Here they're saying, hey, you have a pressure drop across this control valve, and then if you go through the whole system, then that's the rest of the pressure drop. And the valve authority, I don't know why they picked N. A seems to be a better symbol for authority, but hey, is that pressure drop compared to the whole system pressure drop. And it should be in a range of 0.2 to 0.5. You'll see different recommendations. Okay, it should be around half of the pressure drop, maybe in a branch. So it's a significant pressure drop. Valve rangeability. The valve rangeability is the maximum flow to the minimum flow. You'd say, well, isn't the minimum flow 0? Then you just have something divided by 0. Isn't that infinity? But often control valves do not fully close. Because if they do fully close and then you let it sit there for a couple of months and then you try to open it, you may have to beat on it with a hammer or something to get it to unstick. So when you specify a control valve, often there's some rangeability specification. It can be 15 to 1, it can be 50 to 1, it can be 100 to 1. See, so the flow at the maximum would be 100 and then it go down to 1. Or the maximum flow would be 15 and it go down to 1. Something like that. That's the range. 15 to 1, 50 to 1, etc. This is much more common, but you can probably buy it. It's a little more expensive for high valve range abilities. So if the range ability is 15 to 1, what is the minimum flow as a percent of the maximum flow? Man, I should cover up these answers. What is it? Yeah, so let's say the Q max, just to sort of put numbers to it, let's say, oh, it's 15 GPM. I'm just saying it's 15 times something GPM. And the Q min, if it's a 15 to 1, would be down to 1 GPM. Hence, 115 is about what percent? It's around 6.7%. So you're not able to cut it off completely for the control valve. You may have an isolation valve that you definitely want to kill it, okay? But that's not different. You have to isolate a system to pull something out and repair it. Then you have those isolation valves. Well, let's take a look now at heat exchangers. So here are some pictures of heat exchangers that are in the engineering building. I took these many years ago. They're just huge. I mean, they're just like the size of that screen that you're looking at, the picture on, or larger. They'll go from the floor up to maybe the top of that screen. And they're finned cross-flow heat exchangers. This is backside, front side. They'll have chilled water going through some of them and hot water through the other. We have 2 piping systems on campus. Here I just show the looping that goes through, so there's multiple passages of the water back and forth, crisscrossing before it goes out. So there's plenty of opportunity for the water to transfer heat to the air that flows across the fin surface. And this is a little tray right here. What do you think that little tray collects? Condensate. And they put a little stick in there, and they have to be careful of that. And they always have these little things they put in there, little sticks that the maintenance people go through and put them in. I don't know how long they last, maybe 6 months. And what do you think it's for? Bacteria growth. Yeah, bacteria growth. You'd probably smell it if you didn't have something in there to kill it. A lot of times they also have UV lights, ultraviolet lights, like in a sun tanning station, but they're always on and they're very high and powerful. If they have a UV light, sometimes you really can't tell that they're on. There needs to be a kill switch that's triggered with the door. You never want any worker to go in there and not know that the UV light's on. They'll just get burnt. So, but it's very effective at killing things and keeping your coils really clean, the UV lights. All right. So we want to talk about that heat exchanger. Here's a question. If the heat exchanger water temperature rise is changed from 8 degree F to 12 degree F without changing, whoops, this is not a rise then, it's a drop. For the cooling load, the water flow rate will be blank of the original value. Man, this is terrible. All right, so think about the heat exchanger. We have a temperature difference, okay, delta T. It used to be 8 degrees F. All right, so maybe it came in at 40 and it went out at 48 degrees F. So there's an increase in temperature. No, it is a rise, isn't it? It is a rise of temperature of 8 degrees across that cooling coil because you're absorbing heat from the air. All right. But then somebody says we've redesigned the cooling coil or we've changed some parameters and now it's 12 degrees F. For the same load, the same Q load, what is the change in mass flow rate of the water? Does the water flow rate, is it 1/4, 1/3, 1/2, 2/3, 3/4, and why? So what you say is, what's the same between them? You have the same cooling load without changing the cooling load. And the cooling load is the mass flow rate, specific heat delta T. So we have the mass flow rate of case 1, specific heat case 1, delta T case 1, the original case, and that same cooling load, mass flow rate case 2, specific heat delta T case 2. So the mass flow rate for the new case is equal to the original mass flow rate times the original delta T divided by the new delta T. So if you had the original delta T is 8 degrees F and it's now 12 degrees F, meaning the water is coming out not at 40, but it's coming out at 2 degrees F, something like that. You don't need the same mass flow rate, do you? And so what's 8 over 12? It's 2/3. That's a significant reduction. It's a 1/3 reduction in the water flow rate. So it's the engineers, design engineers for high efficiency systems are always trying to get that delta T up. I mentioned it before, but here it is in more detail, right? All right. Flow rate measurements. This is a non-trivial topic. You need to be able to measure the flows. You may think, come on, this should be easily done. No, boy, you wouldn't believe the problems out there in practice associated with flow rate. It's very practical and it's very important. A lot of times it's measured with this. Why? Because sometimes, like in our plant, the employees over there in the thermal energy plant are not UTSA employees. They're contractors. And the contractor is paid by UTSA per how much cooling they provide. And so they're paid on GPM delta T of the water, as well as steam. There's a big contract, and it's been very successful, and that's been in implementation for a long time, and multiple campuses in the UT system operate that way. So I remember a couple of years ago, they had a question because somebody finally looked at the flow meter and said, you know, you have a bend, and then you put the flow meter right there, and then you're going on with the system, but the specs on the flow meter says you need to be 10 diameters back from the bend. You're not. And so what is the effect on the, and so they had long drawn out, because it translated into tens and hundreds of thousands of dollars of accumulated difference in charges. And so this is a very important and practical topic. Sometimes, I hate to say it, when you go out into the facility, there's a line, right? And there's water in that line. Okay, it's just like I can look up here and say there's a duct, there's some air ducts, I can see them. Which way is the air moving in that duct? Which way is the water moving in that duct? And you would think, that's pretty, I mean, they even paint a little arrow on the outside of it to tell you the direction of it, but sometimes it's a little different in practice. So engineers have to be book smart, but also street smart or shop smarter, out there in the practice smart. Okay, but how do you measure flow rate for water? You could do it for air as well, but you have typically a venturi meter, flow nozzle, orifice plate, rotometer, and the list goes on, and those are direct measurements. Then you have some ultrasonic indirect measurements. You don't have to put anything in the flow and disturb it. So there's a lot of people doing a lot of work and valuable work. I'm sure there's a lot of successful careers in engineering and flow metering. So what's a venturi meter? You just reduce the cross-sectional area. What's the flow going to do? From Bernoulli's, what's the pressure going to do? Drop. You have accurate measurements of your cross-sectional shape of your meter. You hook up a tube. Here they're showing you manometer, pressure. Here's a linked manometer. And so the pressure difference and the cross-sectional areas, you back out the flow. It's that simple. Here's another one. So what you have is a nozzle, so that you can see the shape of this nozzle, and then it just abruptly stops. So what's going to happen is you're going to shoot out and you're going to have a pressure drop. It's going to be a much more significant pressure drop than a venturi meter, hence it may be more accurate. But now you're going to have to pay that penalty of always overcoming a pressure drop just to get a more accurate measurement. But you have a pressure tap, and a pressure tap, you could hook up a manometer, measure the delta P, and then correlate that with the flow rate. And then also, I don't think I show it, but you have a orifice plate. I don't think I have an orifice plate. Well, the orifice plate's going to be easier to install, cheaper and everything, but it'll have even more of a delta P, more significant pressure drop. You'll have to pay more in pumping costs just to make that measurement continuously. But it's the same thing. Measure the delta P across the orifice plate. Let's talk about check valves. So what's a check valve? Did I tell you the story that we had a problem when I was first married, and put a little work order in for the apartment complex, and I said, I think the check valve is not working. And then we got a little response from the technician, checked valve, it works. He didn't even know what a check valve was. Seriously, checked valve, it's still installed, not leaking. It's like, no, it's not working. It's not preventing backflow. So basically, it's a mechanical valve that permits gas or liquid flow in one direction only, and if it tries to go in the opposite direction, it will prevent it. That's what a good check valve is. They're all over the place. Anybody have a well? Maybe you're all on the city water service, but you have the submerged well, and it's way below the ground surface. And if you didn't have a check valve, right in here, the water pump, the submerged well would kick on. You would push water up. It would go into the system, but then when it would stop, it would tend to drain the whole thing. And then it turns on again. You got to fill that pipe and push it up and out. No, they're going to put check valve. So the motor stops, or the pump stops, and the head of water sits there waiting. And then when it turns back on, it pushes it out. There's check valves all over the place in very practical situations. But they're very simple. They just stop the backflow. There's a backflow prevention devices. They come in all kinds of shapes and styles. A lot of times you can see these above ground if you just drive around and look. It's like, hey, that's a backflow prevention device. Or in the building, an engineering building, every building that has water service hooked up to it has something like this. What is that? Backflow prevention. City Public Service, no, SAWS, that's right, they supply water. So San Antonio Water System, when they give you a gallon of water, they never want it back out of your building because they don't know what you did to that gallon of water when it was in your building. And I'm so glad that they're not taking back into the distribution system stuff that's been in different people's homes or buildings, because who knows what's going on with that water. So these are all over the place, these backflow prevention devices. I didn't think I'd have time to really go into the detail, but they're like a check valve. That's what they are. Now I want to talk about the last topic for today, and it's a lead in to next time, after the exam, when we move into heat transfer. You have this heat exchanger. It's a heating coil or cooling coil. And let's talk about hot water, and you have cool air flowing over it. And you want to control the amount of heating that actually goes into, let's say, Q dot heat transfer from the hot water into the cool air in that heat exchanger. It's an air to water heat exchanger. You say, this is a pretty easy job. Yeah, I know it's pretty easy. A lot of people have studied it, mastered it, but let's get exposed to some of the challenges in it. Basically, the emission, that's a term for like what is the rate of heat transfer in maybe BTUs per hour, from full operation of that device down to 0% operation of that device. Maybe it's supposed to transfer, you could think of 1 ton or 12,000 BTU per hour. Okay, that will change as the flow rate changes. What flow rate? This is the GPM of the hot water. So if you're giving it 100% GPM of hot water and the air flow rate's not changing, you have some air coming in at 60 degrees F, you have the water temperature coming in at 200 degrees F, and the design is to have a water temperature drop only of 20. So there's, just like the chilled water, you don't have this massive increase in temperature. The chilled water, you don't have a massive decrease of the temperature of the hot water. So it goes out at 200 and comes back at 180. Okay, and then you're pushing it around in a loop. So, but what happens if you don't give it 100% of the flow rate, but the airflow rate hasn't changed? Constant airflow rate. Well, you would think that, it went from 100 to 80% of the water flow rate. I must be down here at 80% of the heat transfer. Nope, you're going to be up at 99 something percent or 97%. If you're at 60%, you would think, hey, 50%, why is it? And the thing is, you have a very nonlinear relationship between the rate of heat transfer, the coil emission getting into the air as a function of the flow rate of the water. So if you're trying to control this, you want to control not just the flow rate of water linearly. What you can do to reduce the severity of the nonlinearity is to put in a larger delta T for that hot water. So it went in, you got to put it in typically a higher temperature, but on delta T of the water go to 60. That'll help straighten it up, but often we're stuck with low delta T for the water. So what do? Well, you have a control valve that has a different characteristic. They have 3 types of control valves being compared here. You have the equal percentage, the linear, and the quick opening. Okay, what are they showing here? This is the valve lift. If you think about it physically, you rotate the valve, typically you spin it and then it lifts off from 0 to 100%, from closed to fully open, or fully open back down to closed. So the valve lift, this is fully open. This is how many spins or seating it. So it'd be the position of some stem that pushes down to seal it. So the characteristic of how much flow you have for the same pressure pushing it across a valve and the valve stem lift depends on the passage characteristics, how it opens up. And so here's just a crude illustration of showing maybe a different design of how that passage will open up as the valve lifts versus how it'll open up. And so what you do is by changing the passageway as it opens up, you can get it to drop off dramatically the flow rate. So if you drop off dramatically the flow rate, they call this equal percentage. That's always very confusing. Why do they call it equal percentage? Well, first of all, the vast majority of the literature calls it equal percentage. So it's not like, oh, one lunatic named it this and it doesn't make any sense. What they're trying to do is, with this type of equal percentage control valve characteristic, is when they start to lift it, they're going to drop that flow rate more significantly, and then the heat transfer will be more linear. So that's the last thing. So we're putting these together. So you have the flow rate through the heat exchanger as a function of the heat capacity of the emission. You have the valve. You want that equal percentage valve shaped like this. When you combine them, you get, for a percent of the lift going from 100% open to 0% open, you get 0 to 100% of the heat emission. It makes it a lot easier to control. Make sense? All right. So that if you have it at 50% lift, you get 50% of the heat transfer. You don't get 50% of the GPM, you get maybe 10% of the GPM, but 10% of the GPM still gives you 50% of the heat transfer. Make sense? Well, with that, I just encourage you to maybe get ready. You can ask me any question right now in the last few minutes in preparation for our exam.
Do you know if the test is going to be open book?
Yeah, bring your book. I may have a closed book portion. I may have a closed book portion and then open book portion. Well, I covered some kind of funny topics today. They're all fair game. And you can write in your book conversion factors. You can tape in your book stuff like a table of conversion factors from another source. And so don't get hung up on units. Yes, you have to convert units. You have to be able to know, oh, how many gallons in a cubic foot? What's a BTU per hour? What's a ton? Yeah, make sure you're up to speed on those units. That's a good question. Thank you. Well, the closed portion would be something like, I've asked this question before. On a blank sheet of paper, reproduce from memory the Moody diagram with as much detail as you can recall to scale. This is like the most important thing in pipe flow is the Moody diagram. And people sometimes get all sort of lost. They think, oh, I calculated a friction factor, it's 22. You know, is there a friction factor anywhere on that diagram, a Moody diagram of 22? Well, I don't know what the friction factor should be. I said, what's the range of a typical friction factor? I mean, do you find a friction factor below 0.01? Oh, well, it could be 0.000. No, it can't. Go find me a friction factor. You know what I mean? So the range of the friction factor is not that tremendous. And then the idea, this is, I'm telling you, I'm going to do it. Thank you for the question. You're going to have a percentage of the exam, which will be a blank sheet of paper, and the statement says, reproduce from memory with as much detail and as accurate as you can the Moody diagram. Because when somebody says it's fully turbulent flow, what does that mean? When somebody says it's transitional flow, what does that mean? When somebody says laminar flow, which doesn't occur very often in practice, we know what that means. But all right? That was a good question. Thank you. I don't like to ask people to look up property values in tables. Usually I give them in the problem statement to save time because time is of essence. But bring your book. Is it okay if you print out one? If you do what? Oh, absolutely. You don't even have to print out all of chapter 1. Any others?